In our last video, I kind of already told you this process, but the point of this short section is how do we find all the zeros of a polynomial function? Well, the first thing we're going to do is we're going to let the rational zero theorem give us some ideas of where we are to begin. So the rational zero theorem is that p over q. So we're going to have all the factors of the p on the back and all the factors of the 4 on the front. So remember, we can turn these over. Where are they doing it here? Okay, so here's the p, and here are all the factors of the q. Now we're doing all the arrangements of p over q, and we create this. So, and remember, the plus and minuses always come in. Now, they immediately jump to synthetic division. To evaluate each of them, I would use the remainder theorem. And especially if you had a graphing calculator where you could put this function in and just keep replacing the x's over and over, that would be much faster. But they're using synthetic here, and they find that 1 is a factor. Okay, well, 1 was a factor because they had a 0 left. So here's what we have now. X minus 1 times 4x to the second plus 4x plus 1, that is now factored. That's what the factor theorem is saying. Now we could take this further. This is a perfect square trinomial where you could do 2x plus 1 times another 2x plus 1. Again, if you need some factoring help, let me know, and I can try to get you some other videos. Okay, so this now factored down, it's completely factored, and here's what they're telling us. So they went ahead and graphed it. So we have a 0 at -1/2 and at 1. Now this one has a multiplicity of 2 because it had an exponent of 2. It's a repeat, so if you don't have to graph it, but if you did, it would bounce. That's what we saw earlier. And at 1, it would go straight through. Okay, so the fundamental theorem of algebra is a very important idea that we're going to look at next. And the punchline is this. If I have a polynomial function of x to the 5th, whatever that degree is, that highest degree, there have to be that many zeros. Now, they don't have to be rational zeros. They could be complex numbers, but they have to add up to have 5 total solutions. So it's a big idea. So if we had had x to the 8th, then we're going to have to come up with 5 different roots. Some of them may be complex, so that's the so it's different. So if a complex root isn't going to show up on the graph, so it's not going to cross the x-axis or touch it, but it has to be a value. So let's dive in here. I'll show you what I mean. Okay, so if we started with the rational zero theorem, we found all the possibilities here. Where have they done it? Here we go. So the front and back, the p is 3 and the q is 3, so I've got plus or minus 1 and plus or minus 3 for both of them. Now we make all of our arrangements and we get down to this. Now again, I think the rational zero theorem, or the remainder theorem is the easier way to test this, especially with a nice graphing calculator. However, that's okay. We will do synthetic division too. That's what they're doing. And once again, they prove that -3 turned out to be a 0, a root. So here's what we've got. We've got it factored down to here by the factor theorem. Now, let's go ahead and solve this. So we know that -3 is a root or a 0. Look what happens when we solve 3x squared plus 1. What we're going to get here are complex numbers. Now, complex numbers are not going to show up on the graph. We're not going to, our polynomial function is not going to hit somewhere at a complex number because of I, it doesn't show up. But look what we do have. We have 1, 2, 3 solutions. Because of the plus or minus, there are 3 numbers here. And our original exponent was 3. So it has to match. Now, again, they don't have to all be real numbers. They could be complex, but the degree will match the number of solutions. So look here, they actually have the picture for us. We only touch at the real solution. We do not touch at the imaginary solutions. They don't show up. Okay, so let's go through this here. My p is 4. So my possibilities are plus or minus 1, plus or minus 2, plus or minus 4. And Q is plus or minus 1 or plus or minus 2. You see that here? So all of our possibilities, so go through all of them, plus or minus 1 over 1, plus or minus 1 over 2, plus or minus 2 over 1. Now look at this one, plus or minus 2 over 2, that's the same thing, so I can ignore that. Okay, so I'm going to run out of space here, so I'm also going to do okay, now here's another repeat, plus or minus 4 over 2. So I just gone through all the combinations, but this is also the same as 2. So my options are plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 1/2. Okay, now I would use the remainder theorem. I would not start just dividing all of these. Let me see here. Yeah, they were really nice to us here. So I'm going to use, so this is what could be super time consuming. Again, you could put this function in on your calculator and just keep replacing the different values of x. But if you don't have that option, I would still use the remainder theorem. And I think if I did this in my head right, we got a hit on the very first one. Okay, so this would be 2 plus 5 minus 11 plus 4. So it just so happened that very first one was a hit, which was nice of them. So 1 is a root. So let's now divide it down. I'm going to use synthetic division. I had to think that through. So when you do synthetic, you use the actual root. So we're going to use 1. I've got 2, 5, negative 11, and 4. Okay, so that was true. So here's what we've got so far. I've got x. Now remember, it changes signs when you turn it back into a binomial. So our root really is 1, but it's like defaulted to a negative sign. So here I've got 2x squared plus 7x minus 4. So now this is factored. That's also what the factor theorem is telling us. Now let's check this one. Yeah, you could guess and check this. I'm going to show you the AC method if you need to see that again. So it's not as simple to factor this because of the 2 in front. So you could guess your way through this. I'm going to show you the AC method where you multiply the 2 and the negative 4. That gets you negative 8. Now we're looking for two numbers that multiply to get negative 8 and add to get 7. Well, they're 8 and negative 1. Okay, so now I'm going to ignore him for a second. So the AC method, let's do it over here. The AC method is going to take those two numbers and turn that middle into those two. So here's what I'm saying. 8x minus 1x. I didn't cheat. That goes back together to get 7x. But I've chosen these for a very strategic reason because they're going to allow me to factor. Okay. Now, if you have 4 pieces with this AC method, you're going to take the GCF of the first two and the GCF of the back two. So I'm just taking a GCF out of those. Now on the back, you have to take something. So there's really nothing to take. They don't really have a GCF, so we're going to take a 1. And if it starts with a negative, you want to take a negative 1. Okay, that is going to flip all the signs when you take a negative 1 out. Now, you know you've done this method right if you have the match, and I do. So the match becomes one of the factors, and the 2x and minus 1, everything else comes together to make the other factor. Now, it's not x plus 4 twice. That was just, we're basically pulling out now a GCF of x plus 4. But what that means is the match becomes 1, everything else becomes the other one. So here's what we've got. In our final factored form, we've got this. Okay, now again, there's not a ton of examples there, but hopefully that's enough to get you started. We're putting together all of the theorems in order to help find our zeros. We learned one additional one, that the degree the fundamental theorem of algebra says that the degree of the polynomial, that highest exponent, there have to be that many solutions. Now they could be real or complex, but there have to be that many.